Welcome, welcome, welcome. We are now on chapter 6, which is all about some very interesting concepts in statistics that are very important, namely the normal distribution and z-scores and z-score transformations. So this is stuff we're going to carry with us through the rest of the semester. Definitely going to want to take notes here. All right, but before that, let's start off with some review. So let's suppose you've got two different distributions of exam scores. And both of these distributions have the exact same mean. But distribution 1 has a standard deviation of 5, and distribution 2 has a standard deviation of 15. The question is, which distribution has more exam scores clustered close to the mean? Well, if you've got a distribution that has a lower standard deviation, and standard deviation is a measure of variability, that means that that distribution has less variability. That means that the exam scores are less different from each other, and therefore they're going to be closer together, right? They're going to be clustered closer together. And that naturally means they're going to be closer to the mean. So distribution 1 is the distribution that's going to have more scores near the mean, and it might be something like this red line in the middle that has low variability, so a lot of scores tightly packed around the mean. Distribution 2 had a much larger standard deviation, therefore it has much higher variability, and it might be something like the green line in this example. For our learning objectives today, we're going to learn what a standardized score is, or a z-score. We're going to learn how those z-scores are actually useful. Then we'll switch over to talking about what the normal distribution is and how we can use the normal distribution to actually test hypotheses about populations. So let's start with a conceptual example. Let's say you might run into this at some point. You want to compare two different things, but they're on different scales of measurement. So think centimeters and inches, and you want to compare those things, or kilograms and pounds, but they're on different scales. So you can't really directly compare those things. And so this example is, what if you want to compare your GPA, and most universities in the US use a 0 to 4 scale, right? But you want to compare your GPA to a friend's GPA who goes to school in France. And in France, a lot of universities use a 0 to 20 scale. And so let's just say your GPA is a solid 3.7 and your friend's GPA is a 14. Well, if you just look at the absolute values of those, like 14 is obviously higher than 3.7, but we want to be able to compare these things in sort of a relative way, depending on what their original scale is. And so how do we go about doing that? And so what we want to do is find a way to put both of these measures on the same scale. And we run into this problem a lot, even in everyday occurrences where, let's take this ruler or measuring stick, for instance, centimeters and inches are not on the same scale. You can put them, side by side, but you can't say that like 1.2 centimeters has anything to do with 1.2 inches or whatever, right? So you'd have to find a way to convert these two things that are still measuring length into the same scale. And that's basically what a z-score can do for us. So now we're talking about a new distribution called the z-distribution. It's called the z-distribution because it's made up of a lot of z-scores. So far in the semester, we've been talking about frequency distributions, and the x-axis of a frequency distribution is just whatever scale of measurement that you're using. If you're measuring people's height, then it's going to be in centimeters or inches, right? The y-axis for frequency distributions was just count. It was just frequency. How many times did you observe those types of data? So like if a participant was 120 centimeters tall or whatever, how many people were 120 centimeters tall? Now we're switching over to the z-distribution, and it has a brand new kind of x-axis, which you'll notice measured in units of standard deviation. That's really interesting. So we'll talk more about how that looks. The y-axis for a z distribution and for the normal curve is now like probability density, and that's kind of a confusing thing to think about. It's sort of related to how many and how often you would see data points at at that level or at that height. So still like higher points in this curve represent a more likelihood that you would see data in that part of the curve, essentially. So it's a bit different than just actual counts. And so again, the whole point of this is to take the raw scores, and the raw score is just the actual data point that a participant gives you on some measure of interest, right? So like the height of one participant is their raw score, 5'5" or whatever. That's the raw score. But in order to compare things that are on different scales, we have to convert all the raw scores to a standardized z-score. And that'll let you put all of these scores basically on the same continuum, the same distribution, so you can compare one to another. Because right now we have two different distributions of, back in our example of GPA, we'd have two different distributions, one that will have some average, maybe it's like 3.3 on a scale of 0 to 4, but then there'll be a completely separate distribution that'll be like, the mean might be 15 on a scale of 0 to 20, right? Those are different distributions, but we want to figure out how to put them on the same distribution so we can actually compare those numbers together. So z-scores are called standardized scores because even though the raw scores might be on different scales, when you convert them into z-scores, they become what's called standardized, meaning they're all along the exact same scale. They use the same scale, the same type of distribution, essentially. Z-scores measure the distance between a data point and the mean. But the z-score in practicality, like if we were interpreting a z-score, it tells you the number of standard deviations away from the mean a value is. The number of standard deviations a value is from the mean. Okay, that's interesting. The number of standard deviations a value is away from the mean. So basically, the z-score is a distance. It's telling us, hey, when we converted the raw score to the z-score, it's telling us how many standard deviations away from the mean. And remember, standard deviation is basically, conceptually, the average distance all scores in a distribution are from the mean. So if you're thinking about, well, what would like 1.2 standard deviations from the mean look like? What would 2 standard deviations from the mean look like? And we're going to talk about those in a second. Negative z-scores indicate that the original raw score lies below the mean. Positive z-scores indicate that this value lies above the mean. And z-scores are really useful because they allow researchers to determine basically where a value is in reference to its mean. Is it above the mean? Is it below the mean? How far above the mean is it? Or how far below the mean is it? So that means how far above average is this point, or how far below average is this point? And also, like we've been saying, z-score distributions are thought of as like standard measuring sticks, and you can compare all kinds of different data sets along basically the same using the same scale. And this is really helpful because, for instance, like in my research, I might be interested in looking at happiness, and one way you can calculate somebody's happiness somewhat objectively is you ask them how well they're feeling right now, like in terms of emotions. We call that positive affect. If they're feeling good, that's like joyfulness. And then we can also ask them about their life satisfaction. And we can use life satisfaction and positive affect and negative affect and combine those in a way that creates a score that we would call happiness or subjective well-being. The problem is that oftentimes positive affect and negative affect scores are on a 1 to 5 scale, and life satisfaction might be on a 1 to 7 scale. So those are not the same thing, but we can translate them into z-scores first and then combine them, because then they'll all be on the same scale. I'll show you what that looks like in a second. And so this is really important. So a z-score, again, it's basically like a unit of distance. It's telling you how many standard deviations away from the mean a particular value is. And what you can do with that information is use it to tell you, well, how unusual or how typical might that value be in comparison to the mean, right? So if a particular value is way different than the mean, like many standard deviations above or below the mean, that means it's probably not a very typical value, because typical values would be right around the mean or would be at the mean. And so it's a really interesting concept of, we can use this now to not only compare where is it relative to the mean, but like what's the chance, what's the probability that we would actually see a value that is really high or really low. And we'll talk more about that later this lecture and next chapter. Okay, so I've been dancing around this, like, well, how do we actually turn regular scores, meaning raw scores, into z-scores, put them on the same scale so we can make comparisons? So let's talk about the z-score transformation. To transform raw scores into z-scores requires that you know a couple of things about the distribution that you're pulling from or that you're comparing to. So you need to know the population mean, which is, again, represented by that Greek letter mu, which is kind of a U that has a teardrop on the left side, or some people think it looks maybe a little bit like an M. You need to know the population mean, and you need to know the population standard deviation, which is that on the denominator, that kind of thing that looks like an O with a little extra line on top of it, or maybe like a messed up 6 or something. That's the Greek letter sigma, right? And so then you have the population mean, population standard deviation, and you have the raw score that you're going to convert into a z-score. And so this formula, the z-score, equals the raw score minus the population mean divided by the population standard deviation. And what this formula essentially is doing is it's translating that raw score into units of standard deviation. That score is away from the mean, because the numerator is saying, well, how far away is this score from the mean? And the denominator, dividing it by standard deviation, is saying, let's convert that not only to like an absolute difference between the score and the mean, but also let's make it in terms of standard deviations away from the mean. Just a quick note that if you wanted to, you could also calculate a z-score for a sample. We've been looking at it for the population and the equation that we've been looking at, x minus mu over sigma. But if you were going to do it with the sample, it would be x minus x bar, the sample mean, divided by lowercase s, which is the sample standard deviation. All right, let's go back to that example of comparing your GPA to your friend's GPA who is in France. So we're going to focus on the first population that we're talking about, which would be all CU students. And let's just say, this isn't quite accurate, but let's just say the mean GPA, the average GPA of all CU students is 3.30 with a standard deviation of 0.30. Okay, now your GPA is 3.70, so that's going to be above the average GPA, and we could ask, well, how far is it above the average GPA? Let's take a look at the graph on the bottom left. All right, so what you're seeing is it's a symmetrical graph, right? It's a symmetrical distribution. So that means that the very highest point, the very middle and highest point of this distribution is going to be the mean, the median, and the mode, right? So it's definitely going to be the mean, 3.30, and you can see that on the x-axis there in the middle, 3.30. Well, if we want to set this up, we probably want to use units of standard deviation away, which we'll get to in a second. But for now, if you were just to add the standard deviation, which is 0.30, to 3.30, which is the mean, you add a standard deviation to that, you're going to get 3.60. Okay. If you were to subtract a standard deviation, 0.30, from 3.30 to the left, you'd get 3.00, right? And so basically this is a way of building out kind of a graph of GPAs based on standard deviations away from the mean. Okay, so now you can see on this graph, if we want to locate where a GPA, your GPA of 3.70 is, I put a little red dash there, right? And we can ask the question like, well, how far above the mean is that in a relative way? Like obviously it's 3.70 minus 3.30. It's 0.40 above the mean in terms of GPA, but we really want to know how many standard deviations above the mean is it. And if you just look at the, just still on the bottom left, that graph, well, it looks like it's a little more than one standard deviation, right? If a standard deviation is 0.30 and you've added that to 3.3, which is 3.6, 3.7 is a little bit more than that, right? So it looks like we're a little bit above one standard deviation. But the way that you would actually calculate it is you're going to want to transform this into a z-score. And you can be like, well, why are we doing all this stuff, right? Remember, what we're trying to do here by converting raw scores into z-scores is so that we can place them on kind of like a standardized scale that we can compare multiple different things that were originally on different scales. Not only can we locate raw scores in a distribution based on their standard deviation away from the mean, but also it tells us how weird is the data. It tells us how weird is that raw score. Like, is it a very unlikely score? Is a GPA of 3.70 way higher than you would expect, given that most students get about a 3.30, right? Or if the GPA was like 1.2, how many standard deviations below the average is that? And then does that make it very, very, very rare and unlikely, right? So that's what we're kind of trying to get at, is how likely is it that you would actually see some of these raw scores? But for right now, we're actually mostly focusing on the comparison point of let's put everything on the same scale so we can actually see whether a GPA of 3.7 is similar to or different or more than or less than relatively a GPA of 14. So we use that formula that I just showed you. The z-score is equal to the raw score that is denoted by x, so 3.70. Then from that we subtract the population mean, which is 3.30, and then we divide that by the population standard deviation. And so if you work out the math, this ends up being the z-score equivalent to 1.33, repeating 1.33333. And that is now, in practice, the number of standard deviations away from the mean that the original GPA is. So a GPA of 3.70 is 1.33 standard deviations above the mean in this distribution. And you can see this in the graph on the bottom right now, which is not a raw score distribution. It's now a distribution of z-scores, so it's a z-distribution. And the units of a z-distribution are standard deviations. Now, an interesting thing is the mean, the population mean of a z-distribution is always 0. And I invite you to think about mathematically, why would it always work out to be 0? Well, in our example, if you have the mean GPA is 3.30, and you subtract from that 3.30, you end up with 0, right? And 0 divided by anything is still 0. So the mean, if you score exactly at the mean and translate that into a z-score, you'll always get 0 because it's 0 distance away from the mean, because it is the mean. And so that's why in a z-distribution, the mean is always 0. No matter what measurement you originally started talking about, when you convert it to a z-score, it'll always be 0. And then the standard deviations are 1 unit, because one standard deviation is the unit of measurement. And so what we see ultimately is that the z-score of 1.33 means 1.33 standard deviations away from the mean. So now there's another red dash where that should go, and it's basically a mirror image, an equivalent of the original distribution, but now it's in terms of standard deviations. Okay, so we found the z-score, meaning the number of standard deviations away from the mean. Your GPA is, okay, 3.7 away from the mean of 3.3. But now we're going to find the same thing for your friend who lives in France, and they have a GPA of 14. Well, the mean GPA at this university that they go to is 15 out of 20, with a standard deviation of 1.25. So now if you look at the bottom left graph, you'll see that the numbers have changed, right? Like the x-axis is now just a distribution of all of these different raw GPA scores. And the standard deviation is 1.25. So again, you can take 15 and add 1.25 to it and start building out like essentially where in this curve the standard deviations are going to be. And you can see where that red dash is, that's where this raw score of 14 would be. And you can see, oh, that's below the mean. 14 is obviously below 15, and this kind of helps you locate it within that distribution. But let's see what happens if we convert it to z-scores. Again, if we take the raw score of 14, we subtract the mean from that, which is 15, that gives us a negative number, negative 1 divided by the standard deviation of 1.25. That ends up giving us a z-score of negative 0.80. So that means that this score of 14, this GPA of 14, is 0.8 standard deviations below the mean. So it's negative, that means it's going to be below the mean. And finally, we have the same scale of distribution. We can compare your GPA to your friend's GPA. So we've created this standardized scale now, and we can put our GPA or your GPA, which is 1.33 standard deviations above the mean. We put that on the graph. We also put your friend's GPA, which is 0.80 standard deviations below the mean, also on the graph. And we can see that without a doubt, your GPA is significantly greater relative to your friend's GPA. You can also say your GPA is above average and your friend's GPA is below average. And you know exactly how much above and below average because it's 1.33 standard deviations above average and 0.8 standard deviations below average. Now the question becomes like, well, how many standard deviations is like a lot, you know? Like, is 1.33 standard deviations above the mean? Does that mean I'm doing really awesome? Like what is the probability that a student would get a GPA that's 1.33 standard deviations above the mean versus somebody who's right at the mean, or versus somebody who has a 3.9, right? That's what we're going to be moving into later in this lecture, as well as in the coming weeks. So as a little bit of review for the z-score distribution, z-scores of the mean in a z-score distribution is going to be 0 because the mean is 0 distance away from the mean. So if you do that calculation, then the mean raw score will always translate to a z-score of 0. it's not at all different from the mean, which makes sense. The standard deviation in a z-distribution is always going to be 1. And you can also plug in a number that is exactly 1 standard deviation away from the population mean. If you plug that number into the z-score transformation formula, it'll give you a z-score of 1, meaning it's 1 standard deviation away from the mean. And so the standard deviation units in a z distribution are always in in increments of 1. The shape of a standardized distribution, meaning a z-distribution, will always be the same as the original distribution. It's going to have the same skew and the same kurtosis, and I invite you to think about why that would be. If we convert all the raw scores into standardized scores, they don't change how far away they are from the mean. We're changing the units and the scale, but they don't actually change how far away they are from the mean, so ultimately the distributions will look identical, not necessarily symmetrical. If the original distribution was skewed, then the z-distribution will be skewed in the same way, but if the original distribution of raw scores is symmetrical, then the z-distribution is also going to be symmetrical. And remember, the point of all of this, again, is so that we can basically compare apples to oranges. We can compare two things that were originally on different scales, but now we've put them onto the same standardized scale, and we can compare them in some meaningful way. So let's end up with some review. Using a z-score transformation, blank the scores from the population they came from to allow us to compare scores between different scales. Go ahead and pause the video and see what you got. The correct answer is B, standardizes. And by standardize, I mean you can take things that have different scales of measurement and you can combine them into the same scale of measurement, which is standard deviations, basically, z-scores. And so you create a z-distribution, and that allows you to compare apples and oranges on the same scale. So here's a free response one. The z-score will tell us the distance a value is from the mean in units of what? The correct answer is in units of standard deviation. It tells you how many standard deviations a value is away from the mean. All right, that's it for this one. I'll see you in the next video.